Hi, my name is Pavel Fatin. I work at JetBrains on Scala plugin for IntelliJ IDEA. In this presentation, I am going to show you how Scala adopts and transforms the classical design patterns. Let's start with the definition. The design pattern is a general reusable solution to a commonly occurring problem in software design. Design pattern is not a fixed code, but it is rather a template that can be used in many different situations to solve a problem. Design patterns are formalized best practices that help us to make our code cleaner, to speed up the development process, and to avoid subtle errors in our design. We must keep in mind that most patterns are object-oriented, and I mean primarily GAN-of-4 patterns, and they describe interactions and structure of objects and classes. Sometimes design pattern might be a sign of some missing language feature, and when a language provides that feature, the design pattern can be eliminated or simplified. And indeed, as I will show you, in Scala we can implement most of the design patterns directly. While Scala employs some language-specific patterns, I will focus on the classical patterns because these patterns are also the means of communications between developers. Here goes the patterns. I will discuss creational patterns, structural patterns, and behavioral ones. Let's start with the factory method. The factory method patterns provides an interface for creating an object, but encapsulates the actual class instantiation in a method, and it lets subclasses decide which class to instantiate. In this presentation, we will use a slightly different version of the pattern that is known as a static factory method that avoids subclassing, so we cannot override the method and we have to do all the instantiation in one place. The factory method allows us to extract some complex creational code into one place, to select which class to instantiate, and to cache objects that we create. Also, we can use the pattern to control access to some shared resource when such resource is limited. Here is a typical implementation of the static factory method in Java. We have a base class animal and two concrete subclasses dog and cat. To implement the factory method, we have to rely on a separate class because we cannot define static methods in the base interface, at least before Java 8. So we define that method that encapsulates all the creation and hides the actual class that we might instantiate. Here's a Scala example that uses a special syntax to declare factory method. And the difference is that Scala provides a special syntax for factory methods. Here we have object animal that is a singleton instance of a companion object, as it is called in Scala. And we define an apply method that can be used in a special way, as we can see below. So it resembles a constructor invocation, and it is a standard way to use such factory methods. And the pros of this approach is that we can reuse base class name. We don't have to define a separate factory class. That is a standard approach, so it is predictable that, and everybody knows that it is a factory method. And it resembles a constructor invocation. And the con is that it is a static factory method, so we cannot override that method. The next pattern is lazy initialization. Lazy initialization is a special case of lazy evaluation strategy, and it initializes some value or object on its first access. So we can defer some expensive computation until the first time it is needed. In Java, we use null usually to indicate that some value isn't initialized yet. And if we want to use such code in a multi-threaded environment, we have to use synchronization. And to do synchronization effectively, we may resort to so-called double-checked locking strategy. So we first check some value without synchronization and then use synchronization to perform the check for sure. And that pattern is known to cause very subtle errors, and it is prone to many problems. For example, that code might produce errors prior to JVM5. And if we need a value that can contain nulls as a valid domain value, we have to use a separate flag, and it can complicate code even further. In Scala, we can do the same in a much simpler way. We use a lazy modifier to declare a lazy value that will be computed on demand. And here's an example. We are defining a value x, and then printing x equals to the system output. And as we can see in the result, the actual computation of the value will be performed only on the last line. So the advantages is we have a very concise syntax. Such values can hold nulls, and such values are thread safe. And the con is that we have less control over the initialization. For example, we cannot get rid of synchronization when we know for sure that it is not needed. Singleton. Singleton is probably the most well-known design pattern in Java, and it is a clear sign of a missing language feature. Singleton restricts instantiation of a class to a single object and provides a global access point to it. It allows us to limit number of classes, of instances of a class, and to implement interfaces, because we have a static keyword in Java, but it is actually not very object-oriented, because we cannot implement interfaces with static keyword, and we have no object that is a parent of static members. So it is a violation of the basic object-oriented programming premise that everything is an object. And we may use singletons to implement lazy initialization. Here's one of many possible implementations of singleton in Java. It is a typical one. It is, I suppose, the first one in Wikipedia. We have a cat class that implements runnable interface and declares a private constructor, so we cannot instantiate such class directly. And we use getInstance method to get access to that single instance, and we can call the run method. There is nothing very complicated here, but again, if we need lazy initialization, we may resort once again to the double-checked locking, and that can be complicated. Scala provides a direct way of declaring a singleton, and that is an object. The code is basically that does the same thing as the previous code, but it is much cleaner. Our intent is clear, and initialization is done on demand, and such code is thread safe. And once again, we cannot get rid of synchronization. Adapter. Adapter pattern converts an interface into another interface that is expected by client. It allows us to integrate incompatible classes so they can work together, and that is useful when we need to connect existing components that we cannot subclass. I mean, final classes and so on. Here's an example of adapter implementation in Java. Usually, that is done by defining a wrapper class that takes one instance as a constructor parameter and implements a required interface, and then delegates all the method calls and converts all data if required. We are using such wrapper classes explicitly in our code. Scala provides a direct concept of adapters expressed as implicit classes. So the code is basically the same, yet we declare our adapter class as implicit. So compiler will automatically insert all the required conversions implicitly. Here's an example. We use our logger instance as a log, and all the conversion is hidden from us. That is an advantage on the one hand, because our code is clean and our intent is clear. We know that it is an adapter. But such syntax might be verbose without an IDE because we don't see the conversion. The decorator. The decorator pattern extends functionality of a particular object without touching the functionality of other objects of the same class. The decorator pattern are useful when we need to express multiple decorations that can be arbitrarily combined together, and when we need to decorate final classes so we cannot resort to subclassing. So basically, decorator is a way to override a method or without overriding a method. Here's an example from the standard Java library, so everybody familiar with it. Here we have an output stream interface and a concrete file output stream class with the buffered output stream decorator. So I will not comment it much because we know it. Scala achieves the same goal by using traits, and traits are basically something like interfaces that can be mixed in. So we can mix in multiple traits in a single instance. And the main feature that allows us to implement the pattern is so-called abstract override modifier. Abstract override means that we can override a method that has no concrete super method in the place of declaration. So we are declaring that we overriding a method, and even we can call superride, yet there is no super method because output stream is interface. So the write method is abstract. And for such code to be compiled, we need to use our buffering trait in the place of instantiation. So we are providing a concrete method that will be override by buffering. And so buffering decorates our file output stream instance. That is a much shorter version and a much more direct approach. And another advantage is that object identity is preserved, because when we use the composition in Java, we hide object identity inside the decorator wrapper. And in Scala, object identity is exposed directly. And the con is that we rely on static binding. So we cannot use the same construct to decorate some external instance. We have to do that only when we call new something explicitly. But that is usually fine when we can arbitrarily combine these decorators in the place of instantiation and not in the place of declaration of our classes. And another con is that we cannot use constructor parameters, for example, to configure the size of the buffer, because traits in Scala have no constructor parameters, and we may use abstract values in stream to do the same. Value object. Value object is a small mutable object that represents usually something like money, dates, colors, and so on. The equality of value object isn't based on identity. Such objects are equal when all the fields are equal. Value objects are very handy when we need to represent all that data, to implement inter-process communications, or when we do multi-threaded programming, because value objects are immutable, so we cannot safely use such objects without synchronization. Java have no concept of value object in the language, so we need to write a lot of code explicitly. Here's an example of point class that contains two integers, and for such simple example we have to define many methods and create hash code methods, string equals methods, and when we change something, for example, at in another field or change the type of properties, we have to update everything that we have written. Scala, because it is a very functional-oriented language, provides many direct ways of creating value objects. The first example is the usage of so-called tuple. Tuples are predefined collections of fixed size that can hold elements of multiple types. And we have a syntactic sugar that allows us to define such tuples in a very simple way. Here's how we can define tuple that contains two integer numbers. And as a description, we can transform that syntactic sugar into the actual instantiation of our tuple class. We can define a type alias if we want, so we can refer to our type as point. Yet tuples are general purpose classes, so even type alias cannot restrict someone from passing something that is not point to our functions and so on. In such case, we may resort to case classes. That is basically an ordinary classes that expose all their constructor parameters as properties. And case classes implement all the auxiliary methods like hash code equals and so on automatically, and such code is automatically updated. So, as we can compare, it is much simpler version, and I found no cons of such approach whatsoever. Null object. Null object pattern allows us to represent the absence of an object, and it usually implements do-nothing behavior. So we can use null objects instead of nulls to avoid explicit checks of reference validity, because null pointer exceptions are very nasty thing in Java. And this pattern can help us to get rid of such null pointer exceptions. In Java, that is usually done by creating a hierarchy of classes and a special implementation that does nothing. In this example, it is a null sound that does nothing. As we can see at the bottom, we don't have to check for our sound that we receive from getSound method, even if that sound is optional. Scala employs the same concept, yet it contains a predefined option type that is a general purpose null pattern implementation. So we can specify explicitly that getSound method may or may not return some sound. So the implementation is just the same, and the difference is that we have to resort to some more complicated usage, because we cannot call methods on options directly. And as you can see, options are tightly integrated with Scala syntax, so we can use for statement to process our sound. And advantages are that our types are clear, so we know for sure that some references are optional. In Java, when we use null object pattern, we still have to think whether that method returns real nulls or null objects, and here we can avoid it and know for sure. And the con is that such usage is slightly more verbose. Strategy. Strategy pattern defines a family of encapsulated algorithms and allows us to vary algorithms independently from clients. So we can select a required algorithm at runtime. In Java, strategy is implemented as a hierarchy. So here's how we can define a base interface for strategy and two concrete implementations of add and multiply strategies that works with integers. To use some strategy in the context, we pass a concrete implementation of the strategy to some context and then call some method so the context can use our strategy. Because Scala is a hybrid language and it supports functional programming, we can use functions directly, and it is a much simpler approach. So basically, it is just the same logic, but notice how we can define our strategies without having to use any classes at all. And it is a very clean way to express our strategies. And we can pass our strategy that is a function into some context that uses that strategy. And we have a type alias strategy that is just a convenience, and we can avoid it and use functional types. So here's a type of functions that takes two integers and return another integer as a result. The advantage is much more concise code and clean code, and the disadvantage is that our strategy type is general purpose, so we can mix all the possible functions without knowing what kind of functions we use. But that might be actually an advantage in some cases, so we can really reuse all the declared functions in our code. Command. Command pattern encapsulates all the information that is needed to call a method later. So we can chain, sequence, or log method calls. In Java, of course, that is done by wrapping our method call into a class or closure, and so we can pass our instance of command to invoker that can run our command and add commands to the history list. In Scala, we can use so-called by name arguments. And by name argument is a special kind of argument that has a special syntax, and everything we pass to such argument by name parameter, sorry. And every argument that we pass to by name parameter are not evaluated in the place of such passing. And we can evaluate some expression or code block by referring that by name parameter, and we can then save that command as a function in the history sequence. So Scala provides a way to defer evaluation of code automatically, so we don't have to wrap anything into some classes or closures. And again, it is an advantage of more concise syntax, and the disadvantage is general purpose type. Chain of responsibility. Chain of responsibility decouples the sender of a request from its receiver, so the request is processed along the chain until some object handles it. And it gives a chance to every object to handle the request. Here's an example of an event handler in Java that have a setter method that allows us to set the next handler, and then it can either handle the request or pass it to the next handler in the chain. In this example, we extracted the sequencing logic in the handle method, so we don't delegate that logic to each element of the chain. Here's how we can declare a keyboard handler that checks the source of events, in this case for keyboard source, and handles that event somehow. We can declare another handlers and then create a chain that will process our requests. In Scala, we can use so-called partial functions that can implement just the same. Partial function is a special function that is defined only for subset of its arguments. So it can either take arguments and perform something, or it is enable for some argument to do the processing. Here's the type alias for partial functions that can process our events. And here's how we can actually define our keyboard handler. Here's a case statement that checks whether we can process our event in that function, and if so, it then performs some processing, and just the same logic in the mouse handler. And here's how we can chain our partial functions with or-else method. So we implement the same logic with the built-in syntax in Scala. And the last pattern I'm going to discuss in this presentation is dependency injection. The dependency injection pattern removes hard-coded dependencies and provides a way to substitute dependencies either at compile time or at runtime. So we can choose among multiple implementations of a particular component and use mock implementations during unit testing. In Java, we rely on composition to implement dependency injection if we don't use something like conversion of control containers and so on. So in simple case, we just pass all the required dependencies as parameters to constructor. In Scala, we have a special kind of relationships that is not composition that expresses has a relationship, and it is not inheritance that is expressed by is a relationship. We have a requires a relationship, and that is self-types, so-called. Here's how we can declare that our trait requires repository. So it does not expose connection to the repository in the inheritance hierarchy, and yet we cannot instantiate our user service without repository. So here's how we can actually inject our dependency when we are creating the user service. So the advantages are clear intent, concise syntax, and our configuration is statically verified. So, for example, when we are using XML, we are risking to get errors in runtime because some dependencies might be misconfigured. And here we have all the static checking. And that is also a disadvantage maybe sometimes. And the full implementation of this pattern, and this pattern is known as cake pattern in Scala, might be a little bit verbose. So that's a disadvantage maybe. So I hope that this demonstration helps to bridge the gap between the two languages and to allow Java programmers to easily gain insights into Scala syntax, and for Scala developers to map the language constructs into the well-known abstractions. Thank you.
Okay. During your dependency injection pattern speech, you mentioned inversion of control pattern and especially container. In Java language, we do have Spring inversion of control, Juice, CDI, and whatever. But what about Scala? Do we have some types of containers here?
Because Scala is tightly integrated with Java, and it is actually compiled in Java bytecode, we can most times use all the frameworks and tools that are present in Java. So that pattern I'm talking about are just addition, and it is not some kind of special and the only way to do the dependency injection of Scala. It is useful because we are not always want to use some external component and something like inversion of control containers in simple applications, and yet we might want to use some kind of dependency injection, for example, for testing.
Yeah, but the question was if in our case we want inversion of control.
Yes, if we want to use inversion of control containers, we may use them, so we can really reuse all the tools.
You mean all Java tools?
Yes.
And there would be no impedance mismatch, like routability?
Most times, yes. So, and that is one of the main advantages of Scala, because we can use everything that we have in Java and gain much more because of the more advanced syntax and functionality. Yes?
As a plugin developer for IDEA, I just wondering what is the most hard feature of Scala to be supported by IDE?
The Scala. So the Scala is probably the most maybe complex language to support because it is a very complicated language and it has a very extensive type system, all the stuff like implicits, and yet it is a statically typed language, so we really need to compute everything. And yes, it is a really hard task to support Scala, and we have not arrived yet to a finish point in this development, but we are trying really hard. And probably one of the features that is the hardest to support is new kind of type macros, because we cannot evaluate all the code to produce some type for highlighting. So that is probably the hardest part. Yeah.
Are they likely going to be implemented?
Maybe in the future they will be implemented, but it is an experimental feature as for now, so we don't have to implement them right now, but that can be a challenge in the future. Yes?
Maybe a little bit dumb question, but in context of this example, if we, what will happen if we declare this user service without database repository, without this part self repository? Will we face compile time error, or will it be runtime error?
Yes. As I mentioned, we have a static check-in, so we will get a compile time error that some dependency is not satisfied.
What happens if user service will have self-save method?
Do you mean can we?
If we add save method to user service, which method
But how to wrap it with those service?
You mean that what?
after create, for example, from before in user service body?
Oh, sorry.
Besides where definition, we are at save method. So if you take user service class and we add definition for save method.
User service, they will have save method.
So what if the user service declares the save method that clashes with the repository service? I suppose that we will get a compile time error. However, I'm not sure.
It's not an override or anything, so we get the compile time error.
If you'll write like override, perhaps it will work.
It has to be that feature that we previously discussed, the override of.
Maybe so. I just haven't tried to do that. So, thank you for your attention.